Good morning, everyone. So let's get started. So a couple of announcements. First, let me just a minute. Just give me a minute. Please just take this. Okay, so one is your quiz, like which was held last time. It will be discussed during the tutorial. So solution of that will be discussed during the tutorial. Second is you will have one extra lecture on this this Friday, because we missed one lecture this week. So this Saturday we will have one more lecture. So these are the two things. And your the third one is your problem set is up, right? So please start doing that. And I think the submission is sometime next week. Okay. All right. So let me see if my pen is charged. I think. Yeah. Good. So let's.
Your extra lecture is on Friday or Saturday?
Saturday, same time, 9 o'clock. Okay. All right. Okay. So let's get started. What we were talking is, or we're going to talk today is regular. Okay. So before regular expression, we will revisit this. Okay. So the theorem which we saw last time was every non-deterministic finite automation has an equivalent deterministic finite automation. There is another theorem which I'm not going to prove, but at least you should know. This is, let's call it NFA continued. Okay. So this is corollary. So it is a language is regular if and only if some non-deterministic finite automation recognizes it. Some NFA right. So we have seen that regular language are those languages which are recognized by DFA. Now this is like coming slightly different. So what is the front forward side? Forward side is the forward side is a language is regular if and only if some NFA recognizes it. That means if the regular language is regular, just a minute, there is some. A language is regular, that means some NFA recognizes it, right? So that is very simple, because if it is regular, then some DFA recognizes it, and DFA is nothing but like a special type of NFA. So that forward side is very clear. Backward side is like if there is some NFA recognizes a language, then it is regular. So if some NFA recognizes a language, that means you can always have a DFA recognizing that language, right? Because from the NFA DFA equivalence. So therefore, a DFA recognizes that language, that means that is regular. So very simple. This is yes. So there are methods to so whether a language is regular or not, and I think we will be covering in next couple of lectures about this. I think next mostly on Saturday we will talk about such method. How do you say that some language is not regular, right? But here we are talking about just regular as of now. So this theorem is I'm not going to prove, but it's very clear you can actually prove, and the book has proved it. Now let's look into something more interesting, which we have already shown, but now with knowledge of NFA, how do you prove this theorem? So these theorems are like, one of the theorem is the class of regular language is closed under the class of regular language is closed under union operation. All right. We have seen this in 2-3 lecture back, I think. And but that time, what we were saying is we do not have idea of DFA, NFA. We only know uh, DFA. And with DFA, we try to prove that if a language is if a language L1 is regular language, then there exists a DFA corresponding to that. If L2 is a regular language, there exists another DFA corresponding to that language. So there are one correspondent between language and DFA. And then what we did is we constructed another DFA, which recognizes L1 union L2. So that's what we did, right? So this is using DFA. But now we know that this we have this theorem, the previous one, which says that language is regular if and only if some NFA recognizes it. So from this logic, let's say if L1 is regular, right, that implies there exists an NFA L1. Says that L1 recognizes L1, right? Similarly, let's call it suppose. Similarly, suppose L2 is regular, then that implies there exists N2, NFA N2, such that N2 recognizes L2. Now, what we need to prove is we need to come up with another NFA, right? Which recognizes, let's call it N. So we need to come up with N, which recognizes L1 union L2, and then we are done. Right? So how do we do that? So very simple in NFA. So what is that? Because we have seen such thing actually already. So let's say I have N1, which recognizes L1, and I have N2, which recognizes L2. So it recognizes means it will have one start state, it can have one or more final state, and some non-final states. And similarly here also it can have one final state, non-final states. So this is N1 and this is N2. N1 is recognizing L1 and N2 is recognizing L2. Right? N1 is L1, N2 is L2. Now what we want is L1 union L2. What we will do, how do we construct it? Very simply, I can add one start state, and from this start state, I will add two null states or empty transitions, null transitions. Right? So this null transition, not empty, this is null transition, and this null transition will go to start state of N1. Right? It will also go to start state of N1, and all the other things will remain same. So there are this. Now this NFA, which is just I have drawn, this will definitely recognize L1 union L2. Everyone is with me? right? So what we are doing is we have two NFAs. One NFA N1 recognizes L1, another NFA N2 recognizes L2. Now what we did is we constructed a bigger, larger NFA, which is N. Let's call it N. And in this N, we added one extra state, that is this start state. Right? And we have null transition to the start state of N1 and the start state of N2. Now, any language you take, which is the union of N1 and L2, this NFA will recognize. Very simple. Any question on this? Okay, so let me ask one question, maybe to get whether you guys are understanding or not. So N is the bigger NFA, right? So what will be the final state in N? Both of N1 and N2. Yeah. So it is the set of final state in N1. Let's call it Fn1 union Fn2. Right. So this is final state of N1. Final state of, right. So union of final states of N1 and N2. That's the final state. And there are the two transitions. So null start state is still 1, right? Start state is still 1, and you can do all the things. Nothing else is changing really. What is changing is you are adding one start state and one null transitions, or let's call it epsilon transition, right? So you can formally also prove it, but I'm not going to show that. Okay, maybe one more question. What will be set of state in Q in N? N. What will be? There is a question why. Why it will be union of these two? Okay. Why it will be union of these two? Because your final state can be anything, right? So either you can go to, even if you reach to one of them, you are done. Other question, okay. Other question I have not answered. This question? What will be the set of states in N? Oh, it will be Qn, Q1, no. Q1 union Q2. Not just that, you also need one more extra state, no? So let's call it Q0. Because if you remember, Q1 union Q2 is this, but then what about this guy? That is extra. So it's Q1 union Q2 union start state. Right? So that's it, I think. Okay, maybe we can try to prove it more formally. Let's do that. So let's call it, let N1 is Q1 sigma delta 1 Q1 F1 recognizes L1, and 2 is Q2 sigma delta 2 Q2 F2 recognizes L2, right? Now what we will do is construct N equal to Q sigma delta Q naught F to recognize L1 union L2. And this is what we are trying to do. Right? So how do you prove it? Like we need to say now what construction means. We need to show that what is Q, what is sigma, delta, Q naught, F. If we can show all of them, we are done. So Q, we have just shown that Q will nothing but it will be Q naught union Q1 union Q2. Right? Q naught union Q1 union Q2. That will be the Q. What about Q naught? Q naught is a start state, so that's there. Q naught is start state. The start state is called the F, right? Sigma is same. Sigma is same. Now, what about F? F, we have just seen that it is the union of N1 and N2, that is final states of N1 and N2, so F1, F2. Last thing, which is the more interesting, is how do you define delta? So define delta so that for any Q, for any Q belonging to Q, right? So this is the any set of that NFA which you are constructing, and any A belonging to sigma. What it should do is as follows. So delta Q A. So this definition is interesting. So this definition, if you look into, if let's go into the diagram. If for these states, right? So this is where my red cursor is moving. For this, it should follow delta 1. For this, it should follow delta 2, right? And only thing is these two things are new, right? So for this, it should follow delta 1. For this, it should follow delta 2, right? And let's look into that. What does that mean? So that means if my Q, if my Q is Q1, right? If my Q is Q1, then I should follow delta 1. If my Q is Q2, I should follow delta 2, right? But if Q is not, if Q is Q naught and A is epsilon, right? Then what should happen is it should, if Q is Q naught and A is not epsilon, right? So if A is not epsilon, there is nothing defined. For this, I'm talking about this case first. This case, Q is Q naught is invalid. Invalid means it should go to null state, right? So there is nothing invalid. It should go to null state. Undefined means it is go to null. But if it is Q and Q naught and A, so then which state it should go to? What will be the thing here? Yeah, correct. So it should go to Q1, Q2. This is it. Q1, Q2. Yeah. So any of these two states it goes. So that's all. So we have defined this, and with NFA you have proved it, right? So now let's look into another theorem, which says that the class of regular language is closed under conjugate operation. The class of regular language is closed under concat operation. We could not prove this using DFA. Tosant has some doubt. Let's first clarify that. So what saying Susant? It should be Q1, Q2, and the states with E transitions from Q1, Q2. Yeah, but yeah, so we don't have to show all of them, right? Because they can indirectly come. So while showing, we can just show that Q1 union Q1 Q2 is what you are going from Q, and then you can define from you can use this if there is some null transition. If you want to define like that using that E notation, that's fine. But for delta definition, this is enough, right? This is enough. And you can actually use the other definitions to go to all other states. This is perfectly fine for the definition of delta. Okay. Next, go to the class of regular language is closed under concat operation. So this is where we stopped while talking about DFA and jump to NFA, right? Because we could not really prove this using DFA logic, right? So the question is, I have two regular language, L1 and NFA which recognizes L1. Let's call it L1. This has one start state, more non-final state, right? This is N1. We have N2, which is another state. Will have one unique start state, more non-final states, and some final states. Right? So this is N1 and N2. So N1 recognizes L1, N2 recognizes L2, and what we want is something which recognizes L1, L2. This is what we want. So how do we do that? It's again very simple. What we can do is we can connect whatever is in N1, the final states of N1 to. So what we need to do is final states of N1 right? And the NFA is really nice for that sense. We can do that. So what we can do is we can all connect all these step with null transition, right? And now this will not be my final state in that construction, right? Because my final state will be only these. Only these will be my final state. Connect F1 to Q2. Yeah, so only N2 final states are final states, not N1, right? So only N2 final states will be final state. And let's maybe quickly take an example to what understand maybe a better way. Like what we are saying, like let's say my L1, just for example, L1 is let's say what ends with L2 ends with 0, 0. Right. So ends with 1, L1. Right. How do you make a NFA out of it? Right. So this NFA recognizes all strings which ends with 1. All right. Everyone with me? This is a perfectly fine NFA. What about the N2? The N2 will be which ends with 0, 0. Ends with 0. Ends with 0. N2, right? N2 ends with 0. What about L1? What does it mean by L1 concat L2? L1 concat L2, will it contain something like this? Let's see. 0, 1, 0, 0. And maybe, right, so ends with 1. This is in with 1 and ends with 00. Right? Or it can be 0, 0, 1, 1, 1, 1, 0, 0. Very simple. I think we took a very simple example. So this is 100. Yeah. So last 3 digits are 100. Definitely, that ends with 100. Correct. So it's not just this, but many more. Ends with 100. So now what we are doing is, how do we construct? We said our construction logic is our start state remains the same. This state we may connect to the start state of the next, right? And this is same 0, 1. And then we have 0. Then we have another 0. Final state here. This is the final state here. All right. So this particular string or this particular NFA will always recognize there is some issue. So ending with 100 is not really correct, right? It's possible. Yeah, 100 is not always correct. It's, for example, let's say, what is this? Let's call it 1. Then we have 0, 0, 0. This is also perfectly fine, right? 1000, it should accept. It's ending with 00. 000 is not correct. 000 is not correct. That's correct. That's true. But 1000 is fine, right? 1000 is fine. So this is fine, and this guy is doing exactly the same. This particular NFA is doing exactly the same. Whatever is the concate of this, it will recognize. Yeah. So this is definitely doing the same thing, right? So this is concat operation. We have just seen how to do that. Now, if you want to formally, how do you formally prove it? Very simple. Again, we need to do the proof by construction. So we have N1, Q1, sigma, del 1, Q1, F1, and we have N2, which is Q2, sigma, del 2, Q2, F2. Now tell me what will be the Q, right? So we are constructing N, which is Q, sigma, del 2, del Q and F. Right? So this is what we are constructing. What will be Q? What will be Q naught? What will be F? And what will be delta? Right? So Q will be definitely Q1 and Q2. Q naught will be Q1. F will be F2. Correct. And del is always a problem, no? So del we need to do slightly more things. Or maybe we need separate slide for that. So del is QA. So del, what happens? When you are in N1, right? So where you are in, so there are different cases. One case is you are in Q1 and Q is not a final state, right? Another thing is Q is a final state and your A is not null. Again, another thing is Q is final state and your A is null. And another thing is your Q is in Q2. Right? So these are the cases. So when you are in Q2, so this one very easy. This will be just del 2. But when you are here means it should be delta 1 Q A. When you are here, Q it belongs to F1 and A it's not null. Then you should do delta 1 Q A. Right? A is not null. You can have such definition. It should not be phi, right? So this is interesting thing here. It is not directly phi, but it is delta 1 QA because you have a loop back to the things. The last one, which is QF1, Q belongs to F1 and QA null. It should go to delta 1 QA union Q2. Why? Why it is so? Because if you remember, let's look into the figure, it's possible that all of these can also have some this type of transitions, right? Who is saying that that's ends there? It's not just going to Q2, right? Final states may have not. It can have these transitions which are non-null transitions, and therefore it is going to that. Right? So right, A is null. So it is possible that the final state is have some other transitions and then union Q2. Any question on this? The last theorem, which I'm not going to prove, but you should definitely do it, is maybe we can just pictorially see how much time we have. We have a lot of time, so we can easily do that. Let's do the last theorem for today. Is the class of regular language, reglang, is closed under star operation. Right? Star operation means you do either a 0 time or multiple time. So what is a star operation? So let's say you have NFA L1. Right? So this is your NFA N1. And what we want is repeated things should be allowed, right? 0 or more repetition is allowed. So what is L1 star? 0 or more repetition of strings, right? So 0 or more repetition of strings. So then the thing is, since 0 repetition is allowed, so your first state should be final state, and then with the empty you can add this. Let's call it Q1. So Q1, and right, and this should do your job. So this will like once you recognize something, right? So some string, when you recognize some string, you will start from here, you will reach here, right? When you reach here or here, when you reach here, you again go to the first step and then repeat that, right? So you are repeating the same thing again and again, and therefore this will do star operation, right? Very simple. And why this is first state is empty state, because you have 0 or more repetition of strings. So this is 0 repetition of string. Connect F1 to Q1 using null. Yeah. Yes. Okay, so I'm not going to prove this formally, but you can try proving, constructing this, because you have N1 given, you need to construct N, and that's not very hard. Okay, so now let's look into something called regular expression. Right? Regex, or sometimes people call it like regex. Regular expression. So these languages, which are like regular language, its regular expression is a way to represent that, right? All this regular language, because this regular language can be very complex, right? So something like ends with double zero and starts with 1. So this type of regular language, how do you represent it? So to represent such thing, you need some kind of a expression, and these expressions are called regular expressions, right? So examples are like, is let's say I have to say 0 or more ones, 0 or more ones. I can simply write this thing as 1 star. 1 star means either 0 time or multiple times, right? So this is a way to represent regular language expression, and this has utility in like all this search, right? So if you do, I don't, so I am hope you might be doing this Linux grep and something. Huh? So something like, let's say I want to search all the files which starts with. So search let's say in your machine, search all files which, or let's call it list all files which starts with an, all right, which starts with, how do you do this? You'll say ls an star, right? But that's, this star and that star is not to be confused maybe. But here the string is, your alphabet is A to G. right? So it should have AN, and then this star is for anything else, right? But here this star is not that the same star, but the notion is, yeah, AN A to J star, right? So AN A to G star. So it should start with AN and then any number of other things. I'm okay. So let's say AN A, AN B B B A, or AN X Y Z, or AN XXX. Anything is fine. When yes, it starts with any, then yes, it starts with AN and then any random string, right? So this is what. So this is called regular expression, and it has a lot of utility in Linux. So, I'm not going to talk that in detail. We are going to formally define what is regular expression. So definition: R is a regular expression if R is, right? R is a regular expression if R is A for some A in the alphabet 2. Right? Yeah, even number of ones. If you did like, but it's not even number of ones, because the thing is even number of ones, but you have zero. If the string, if your alphabet is only one, then that is correct, right? We'll see such examples. Let's concentrate on the definition. R is a regular expression if R is some alphabet, right? Or it is empty, or it is null, right? Empty and null are two different things. Empty is a symbol, and null, high, is nothing, right? Fourth is R1 union R2, right? Where R1 and R2 are regular expression. Fifth is R1 concate R2, where again R1 and R2 are regular expression. Or sixth is R1 star, where R1 is a regular expression, right? So these are the six things which makes something regular expression, and anything else is not regular expression. Only these things are the regular expression. So it should be either a symbol, the alphabet. It can be null. It can be sorry. It can be null. It can be empty string, or it can be union of two regular expression. The what you call is concate of two regular expression, and star operation of a regular expression is a regular expression. And let's take first, let's do some examples to understand this. And another thing is, like when you say A star, that means zero or more repetition of A. Right? There is another thing which is not for convenience. So the definition does not include, but for convenience we use it A plus. A plus means one or more repetition of A. Okay. So let me take an example. Example. One star 0, 1, star, star, right? 0, 1 plus star. What will happen? So this is a regular expression. Now this regular expression, first question is, can it contain empty? No. It can, right? Because 1 star means 0 repetition of 1. This star means 0 repetition of this guy, 0, 1 plus. So this has means you can have nothing at all, right? So it can be like the empty empty string as well. But is the question is, can it contain, let's say, 0, 1, 0, 1, right? Can it contain 0, 1, 0, 1? Yes. What about 1, 0, 0? Can it contain 1, 0, 0? No, right? So it can contain 1, 1, 1, 1, 0, 1, right? And at least 2, 0, 1, 0, 1, 0, 1. Yes. Yes, right. So what actually can be written is every 0 in W is followed by at least 1, 1. But yeah, more than that. More than that. Then the question is, let's say 0, 1, 1. Is yes or no? Yes, right? Because why yes? Because 1 star we have ignored. We have taken 0 instance of 1, and then 0, right? So that's 0, and then we have 1 plus. 1 plus means any number of 1, 1 or more number of 1. So therefore, this is 1, 1, 1, 1, 1. Is fine. And then we could have done multiple of this if we apply a star, but applying a star is up to you. How many times you apply, right? So this is perfectly fine. So in English, if I have to write this is nothing but all W's such that every zero in W is followed by at least 1, 1. H. Y. Paste. Right. Every 0 in W is followed by at least 1, 1, but it can have more ones as well, right? And it can start with 1 or. So this may not be the complete definition in us as such, because it is a correct definition, but this is also correct if I just include this part. So 1 star is like 1 or more instance of 1. Okay, so we will see more examples in the next class. We also have some small class participation type questions on this. Do practice. So there are enough examples in the book to practice it. Very interesting concept, and you can really. Okay, so that's our question. R1 intersection R2 is not a regular expression. Is that so? Anyone? So we'll discuss this in the next lecture, whether R1 intersection R2 is regular language or not, a regular expression or not. And specifically, since we have not considered them that in the definition directly, So we should definitely discuss that. So we'll just do that. All right. So with this, we will stop here, and we shall meet tomorrow